If you've coded in Python before, you've probably come across the main Python libraries. Two of the biggest examples, of course, being NumPy and SciPy. These examples are used extensively in the scientific community, and for a good reason. They provide many important functions that are used all the time in scientific research. But compared to what we're about to explore, they're nothing. With the right tools, you can take a simulation of 400 particles and turn it into a simulation of 10,000 particles, but at no extra time cost. The secret, of course, is proper utilization of computer hardware, and more specifically, the GPU, which most people have access to these days. Welcome to the first episode of the GPU Accelerated Python series, the Boltzmann distribution. So the general idea behind these videos is I'm going to be taking code that I wrote in an older video. In this case, it's the Boltzmann distribution code. I'll put a link to that video in the description, and it'll be on the right-hand side here. And then the new optimized code will be on the left-hand side here. And then you can actually see how much faster something like PyTorch, in this case, makes the code run on a GPU. I should say, by the way, in this video that the graphics card I'm using is a GTX 3070. So depending on the speed of your graphics card, maybe you have a faster one or a slower one, the code might run a little bit faster or slower, but the 3070 is a pretty, mid-range graphics card in terms of, the sort of things that scientific researchers will be working with. So the first thing to note is the imports, and you'll see that I have a few more imports here and less here. So in order to get this GPU boost, we're going to be using the machine learning library PyTorch. And so that's, exactly what you might think of it. You think, okay, PyTorch, that's machine learning, that's training AI models, etc. Well, the reason why PyTorch is so good at that is precisely because it uses the GPU. And if you go into the back-end functions that PyTorch uses, they're all optimized functions for, linear transformations and things like that. And you can borrow those into other applications. In this case, we'll be looking at it directly. But there are also libraries that build, fast integration, fast other things on top of PyTorch. So today we're going to look specifically at PyTorch and how it can help for this simulation. But in future videos, we'll get more into the other functions. So I'll import my libraries here and I'll import it here. So this is the new code, the fast code here. And so remember that what we're doing here is we're simulating the Boltzmann distribution. So the question is, what is that? Well, the idea is that if I have a bunch of particles in a box and they're all sort of flying around and bumping into each other, what happens over time is that their velocity, the distribution of their velocities, so the statistics of their velocities, approaches what's known as the Boltzmann distribution. So no matter what initial state they're in, you can have a bunch of them coming to the right at 500 meters per second, a bunch of them going the other way at 500 meters per second, and they start in a random state, but after colliding with each other and bouncing off the walls a bunch, it will always approach a certain distribution. And so you can actually perform a simulation of this and prove it. And so that's what we'll do here. And so the idea is that you need to simulate a number of particles in this box, simulate them colliding with each other, bouncing off the walls for, an extended period of time, and then look at how the distribution of their velocities changes over time. So in each case, we'll take 16 particles here, and we're going to randomly initialize their positions. Now in this case, we're going to be in a 2D plane. It's not a box, it's like a square. They're all confined in the square. And so what you need is a random X and Y coordinate. So if I have 16 particles and I randomly assign a bunch of particles here using the torch.rand function, you can see that my R is going to have a bunch of X coordinates and a bunch of Y coordinates, 16 values each. Same thing here with NumPy. I do the exact same thing. It's just a different function. So first thing to notice is I'm using torch.rand the same way I would use numpy.random.random. And so what that does is it uniformly distributes the particles in the square. And what I do is I give certain indices to these particles. So whenever a particle is greater than 0.5, so by the way, these particles are distributed between 0 and 1. So the ones that start to the right, I'm going to call these index right, and the ones that start to the left, I'm going to call it index left. So I'm keeping track of which particles started on the right and left-hand side. The reason for that is when I make an animation of the simulation, I want all the ones coming from the right to be red and the left to be blue, and then you can sort of see how they all mix in together. It's just a little visual feature. And I do the exact same thing here. So now I have my indices as well. So if I look at index R, And notice it's a tensor, it's a PyTorch tensor. So it basically tells me these ones are on the right, and then the index left, of course, tells me which ones are on the left. So I get the same thing. Same thing here, only with NumPy arrays. So this is the slower way of doing things, of course. Not so much at this point because I only have 16 particles. But I'm also randomly sort of putting particles in places, and I have my index right and index left of where the particles came from. So the next thing we're going to do is we're going to give an ID to each particle. So there's 16 different particles. There'll be 16 different IDs. And so here I use the torch.arrange, and it just basically generates a list from 0 to 15. These are going to be the IDs of the individual particles. And again, torch.arrange is analogous to numpy.arrange. So I can also generate the IDs in NumPy, the slower way, like this. And I also get my thing here. Notice that this is a tensor, this is an array. And the tensor is an object that can live on the graphics card and speed it up quite significantly. So now I have my initial particles randomized in the box, and I can plot the initial configuration of them just by doing a scatter plot with all the locations of the particles. So here I can make a scatter plot. You can see that in Torch, for example, I have to convert to CPU before I plot. So I've assigned that I'm using my graphics card here using PyTorch. And so whenever I plot something, you have to take it off the graphics card first. So I use .cpu. That allows me to plot this tensor, well, not this tensor, but this tensor here, which lives on my GPU device on the plot here. So that now I have my plot of the particles. And I can do the same thing in NumPy. Notice that in NumPy, I don't have to call CPU. So I have my particles on the right starting as red and the left starting as blue. So that's my starting location. And eventually I'm going to need to assign velocities to them, and we'll actually create the simulation. So again, same thing on both sides. We're going to sort of initialize the velocities of the gas, and we're going to make all the particles on the right-hand side move to the left at 500 meters per second, and the left-hand side, they're going to be moving to the right at 500 meters per second. So you have these two gases colliding with each other, and then you'll show that over time, even though all the particles have a speed of 500 meters per second, it will eventually distribute in such a way that the distribution of the velocities is according to a Boltzmann distribution, which we'll get to. So the way to do that is, well, okay, I initially assign all the velocities as 0, right? So if I just look at the shape of this tensor, V, notice that it's shape 2 by 16, because that's how many particles I have. So I can look at v.shape, always very useful in both NumPy and PyTorch. So these are the XY coordinates of all 16 particles. Then what I can do is I can say, okay, I'm going to take V0. So V0 is going to be the x velocity of all these particles. So right now it all starts at 0. And at any of these indexes, remember these IXR is indexed to the right. So I index this array, only the values at these indexes, so only the points at the right get a velocity of negative 500 meters per second, and to the left get a velocity of 500 meters per second. So if I look at V after running this cell, you can see that some of them are moving to the right at 500 meters per second and others to the left at 500 meters per second. And that depends on their location. So if I confirm this with R, you can see that, of course, this one starts at the left because it's less than 0.5, so it moves to the right. Whereas this one is starting on the right-hand side. It's a little bit greater than 0.5, so it's moving to the left. So useful way to understand these arrays. So of course, this here on the left was done with tensors. On the right-hand side, it's done with NumPy using the np.zeros. So you're starting to see that every function in NumPy is analogous to a PyTorch function, which is really handy when it comes to taking code that's initially coded in NumPy and converting it over to something like Torch for that huge speed boost. So this is probably the most difficult part of the simulation. Remember, we have a bunch of sort of billiard balls in space. They're traveling towards each other and they're going to collide with each other. And when they collide, they're going to transfer momentum to each other. That's how the speed of the particles changes, and that's how the distribution of all the velocities approach the Boltzmann distribution. So we need to determine, for example, if two billiard balls are going to collide with each other, of course, in both cases. And so you have to think, okay, well, how am I going to keep track of this? Because basically what we'll do is we'll run a simulation where we advance time a little bit, they all move a little bit, then we check to see if they've collided with each other. If they haven't collided with each other, then we move them again, move them again, move them again. And for any pairs that are colliding with each other, we need to send them going in opposite directions. So we advance time a little bit at a time. We check for particles that have collided with each other. And for those particles, we change their velocities. So in order to determine if two particles collide, you need to find the distance between all the different pairs of particles. So that's important when you consider all pairs of particles. So if there are n particles, there's going to be n times n minus 1 over 2 pairs. That's just simple combinatorics. So if I have 16 particles, I'm going to have 16 times 15 divided by 2. So 8 times 15 is going to be 120 pairs. So you see why these simulations get complicated. If you're simulating 16 particles, you already have to keep track of all these different pairs and the distances between all these different pairs. Remember, we need to keep tracking of all the different pairs at once. So for 16 particles, if I have 120 different pairs, I need to loop through all 120 of those pairs and check to see if the two particles are within colliding distance every time. And so that can be difficult. And so this is combinatorics. And to make this easier, we'll get pairs of particle IDs. This is just so to understand at the beginning and also to compare the two functions. So this is really in some ways where the real speed up comes in PyTorch with large numbers of particles. So you'll note that in the NumPy case on the right here first, I use this combinations function. So what it does is it takes in this list of IDs, just the IDs looks like this, and it's going to give me all possible pairs of IDs. So I convert it to a list, and then I convert it to a NumPy array. And so to give me, for example, 0, 1, because that's one pair, 0, 2, 0, 3, 0, 4, all those sorts of things. And of course, if I look at the actual array, it does give me exactly those things. So it's the pairs of all the particles. In this case, it's the pair corresponding to the index of that particle. Now, it turns out that PyTorch is a function that does that exactly as well. So here, IDs is the tensor, and it's also going to give me the pairs of all particles. So instead of having to use this combinations function, I can use this built-in PyTorch function to do this. And sure enough, it gives me the exact same thing. Remember, this is an array. It lies on the CPU, whereas this is a PyTorch tensor. Of course, it has the option to be on the GPU, which is exactly where I add it. So I go .to device, and that puts it on the GPU. So any operations I do with this are going to be very, very fast. So remember, in the simulation, we need to consider the distance of all pairs. If we're running a simulation where we advance time, we need to be looking at the distances of all the pairs. And then for any pairs that lie within a certain distance, when the two radius of the balls or the billiard balls touch, whenever we get less, their distance between the centers is less than the 2 times the radius, then they collide with each other. That's sort of how billiard balls collide. As soon as the distance between the centers is twice the radius, they're going to bounce off each other. So that's how we need to simulate here. We need to check for that every sort of iteration of the simulation. And so we need to ask, how are we going to do that? Well, the first thing we can do is we can get the pairs of all x positions. So remember that R0 gives me my x position here. And if I want the pairs of all x positions, well, I need to get the combinatorics the same way I did with the particle IDs with this array here. And so what I can do there is I can use the same combinations function as above. And sure enough, I get the x pair distances. So this gives me x1 of one particle and of the other particle as well. And it corresponds exactly to the IDs pairs as well. And again, I do the same thing in NumPy here, and I get the same x pairs. So if I want the distance delta x ij between particle I and particle j, all I need to do is take the difference between these two values here, and that gives me delta x between particle 1 and particle 2. So if my particles are here, delta x gives me this distance here. And so I just use the torch.diff function. All it will do is it'll take the difference between these two elements. So I index along this axis equals 1, so it takes differences along this axis, and then I unravel it to get a 1D array. And this will give me an array of the sort of distances between all particles, all pairs of particles. So remember, I only have 16 particles, but my distances array is going to be much larger. So now the total distance, well, I need delta x of the pair plus delta y of the pair squared. This gives me the Euclidean distance between the pairs. And whenever this distance between the pairs is less than twice the radius, we know the two billiard balls collide, and we have to send those two ones in opposite directions. So sort of going by all the code that we did above, I get my x pairs and y pairs, dx and dy, and then I just, take the sum of the squares, which is the Euclidean distance, and I get the distance between all my pairs of particles. And remember that these pairs, these distances correspond to all the different ID pairs as well. IDs pair, I think I called it. So for example, this distance here corresponds to particle 0 and particle 1. Or for example, this distance here, you'd have to scroll down and find the corresponding pair that corresponds to. So these distances give me the distances between all pairs. And I need to look, every time I run the simulation, I need to look at all these distances, and whenever this value is less than twice the radius, I need to make the particles collide with each other. So the next question is, once these particles do hit each other, what's going to be the corresponding velocities afterwards? In other words, if you have two sort of objects collide with each other in space, how do you use momentum transformation for spheres? Remember, the spheres are going to hit at a certain angle. What do their final velocities look like? Well, I'm not going to go into the physics, too much depth here, but you can show, and this would be a good exercise with spheres and geometry, that the final velocity of the two spheres, well, the first sphere is going to have this final velocity, where you take your first velocity and your second velocity, and the corresponding positions as well of the two particles, and you can get your new velocity for sphere 1 and your new velocity for sphere 2. And so this holds obviously in both simulations. And so, for example, if I set my radius equal to 0.06, and I want to know which pairs are colliding, I can use my d pairs array. So this is the distance between all pairs. And I look for values where it's less than 2 times the radius. So if I go like d pairs is less than 2 times 0.06, it will give me the location of the billiard balls that are already colliding with each other. By the way, this is bad if they're colliding with each other before the simulation starts. It occurs for when the particles of the gas are sufficiently large. So 0.06 is actually a large radius here. But basically, every iteration of the simulation, it will tell me whether these are colliding with each other. So I need to pay special attention to these indices here. Notice that I use the exact same notation in PyTorch and NumPy to get these. So in this case, this is giving me the pairs of the particles that are colliding in this simulation, which is done on PyTorch, and this one in NumPy. So I just reran the simulation. There was a little bug here with my computer, but now the indices of the ones colliding on the left are 0, 2, 3, 4. The ones on the right are 1, 8, 5, 11. So sure enough, if I index my velocities and I actually look at the corresponding new velocities, you can see that these are going to be the corresponding v1s and the corresponding v2s of the particles that are colliding. And of course, I can get my positions of the r1s and of the r2s. So then we basically just use this equation here above. Of course, in this case, note I'm using the torch.sum function. In this case, I'm using NumPy functions to apply this operation. Then we basically just use this equation here to compute the new velocities. Here, of course, I'm using torch functionality. Here I'm using NumPy functionality, but it looks very similar. So now we basically have all the functionality we need to perform the simulation. Everything that I include in these functions here is stuff that we've done before. So in this case, here's like getting the distance between the pairs using that combinations function for both NumPy and torch. This function just computes the new velocities, given sort of these old velocities and old positions here. The only thing we're adding here is the motion. So this is something that is going to be called every sort of iteration of the simulation where you slowly moving the particles and colliding them, etc. So here I'm going to store the position of my particles at all times, because eventually I'm going to want to make an animation of the simulation. So right now I start it as just empty. Same thing here in NumPy. You can tell the difference between the two functions. My initial state is going to be the initial state of r here. So that's the randomized state that I specified above. Same thing with the velocities. I also pass in the ID of all the pairs, the number of times that I want to simulate. So maybe I want 10,000 iterations. The delta t between different iterations, maybe it's like 0.0008 seconds or something. And then the d cutoff, which is basically 2 times the radius of the particles. Then what I do is I loop through for each iteration of the simulation. I get all the IDs of the colliding pairs. So that's IC for collision. I set the velocities at these corresponding indices equal to the new velocities. So I'm updating part of that array based on these collision IDs. It's the same sort of thing I was doing here to get the values of the arrays. And then what I do is, if they're hitting the sides of the box as well, I have to adjust it. So anything that tries to pass outside of the box, well, it gets negative velocity. So if it has positive velocity and r is greater than 0, it's just going to reverse its velocity. Same thing for the left-hand side of the box and the top and the bottom. So this is something new as well. Again, you can see the corresponding functions in NumPy. It basically looks the same, only I'm replacing torch with NP. So you just have to know which torch functions to use. So I can define these functions in both cases. Then I basically define the radius of my particles. I set d cutoff equals 2 times the radius. I set a very super small delta t, and I simulate for 1,000 different time points here. So not super long. But again, remember, I have to keep track of many particles. So here's where you have to start paying attention to the computation time. And it actually won't make a difference, or it might even be worse for PyTorch for small numbers of particles, because there's an overhead associated with using the GPU. So if I run this a few times, just to get some statistics here, you can see it takes almost exactly 2.1 seconds to run each time. And let's look at NumPy. In fact, here the radius is a little, let me set the radius the same size, just for consistency. Look at that. That is interesting. It runs, 20 times faster for NumPy than PyTorch. And I'm here claiming PyTorch runs faster than NumPy. And so someone who, does this, okay, we have our simulation. We've shown that NumPy runs a lot faster. Why use PyTorch? Well, you have to remember there's an overhead with this. And it turns out that as you ramp up the number of particles, the GPU actually does become way more efficient. And I'll prove it to you. But as you can see right now, this is very interesting. NumPy seems to run faster, 0.1 seconds versus 2 seconds. But don't worry, I'm going to show you that PyTorch is indeed much faster. Maybe not for 16 particles, but definitely for 40,000 particles. So this is just a little plotting script. This is just going to plot circles on the screen showing the locations of all the particles. So, this is just some code here. I don't want to get too much into the actual animation here. If you're interested, you can look in the code that I'll put in the description below. There's some code here as well that I have to make an animation of the simulation in both cases. So I'll run that, I suppose, for both cases here. Now, I should note that here, I'm using a much better animation plotting script than I did here in my old video. This is because I'm using the technique of blitting. So this whole series is about optimization. Blitting is a way of only redrawing things on the new frame that have changed. So in this case, only the positions of the particles have changed, so I don't need to redraw the axis every time. And here I'm not using blitting, and it makes a big difference for, large animations especially where there's a lot of different things on the screen moving around. And so again, we can actually look at this animation. I'll just show it here. So you can see the particles are colliding with each other and bouncing off the walls, and, it looks just about right. Sometimes you get this issue where two particles, when they start in the same position, they become connected like that. And that's because they start with their radius less than, like their initial position, they're inside of each other. That can lead to glitches. That usually happens for simulations where the radius is pretty big here. And there's ways to fix that if you're clever, but I didn't want to get too much of that into this video. But for many, many, many small particles, it doesn't matter as much. So now we're going to make a simulation with many more particles. And what I'll do is I'll start with 400 particles each. And all I'm doing is I'm running the same simulation above, except with 400 particles in each case. So I showed you that NumPy runs 20 times faster than PyTorch, which is, I claim, runs faster. So that doesn't look good for me right now, but watch. As I run up to 400 particles, it's going to run faster. Reason for that. Okay, remember 400 particles, I need to keep track of basically 400 squared different pairs. So the computational burden goes up as a factor of n squared for the simulation. So let's first run it in NumPy and see how long it takes. And I think it takes about 40 seconds, so I'm going to skip to the end. Okay, so the simulation just finished in NumPy. It took about 48.5 seconds. So not the end of the world. I mean, 50 seconds, that's pretty, reasonable in terms of if this was the total number of particles you wanted to simulate for all intents and purposes. I mean, sure, it's fine. Now, let's go to PyTorch and see how long it takes to run. 2 seconds. So 2 seconds versus 48.5 seconds. Okay, and you think, all right, well, what does it really matter? Why not just wait an extra 40 seconds for your simulation? I mean, it's not that much of a speed boost. You could just, 40 seconds, things take way longer anyways. But the real power here is, okay, maybe it's as fast for 400 particles, but let's now do 10,000 particles. And let's see how long it takes to run. Okay, so look at that. This is beautiful. You can see it took about almost exactly the same amount of time as the NumPy simulation. Only we have 25 times more particles in this case. So you tell me which one is better. And by the way, this is super important to sort of illustrate where GPUs become important. Because you saw above, okay, like this is doing 25 times more particles, same amount of time. Whereas here, it took 2 seconds, and here it took 0.1 seconds. That's awfully confusing. This one is like 20 times slower. And again, there is an overhead for using GPU. But when you have powerful simulations like this, where many things are happening at the same time, it speaks for itself that you can do 25 times more particles compared to NumPy. And not a lot of people know about this. That's why I'm trying to put these videos out there, is that, for a while I was like that too. I thought, okay, NumPy is the most optimal way of doing everything. Well, obviously that's not the case if you have good hardware. So it's so important to look at your task and think, can I use a GPU to sort of speed it up? And if it's, where you're doing a lot of simulation type work, the GPU is just essential. So, okay, and I want to show you sort of why this 10,000 particles is better for showing that it approaches the true sort of Boltzmann distribution. So remember I said the speed of all the initial particles was 500 meters per second. They move around, they collide with each other in the box, and eventually it approaches some sort of distribution. That probability density function is equal to f of v, this PDF, and it's basically a normalization factor times v times e to the negative v squared. So it's a function that looks like x e to the negative x squared, kind of, with some proportionality factors here. Same thing sort of here. And so what I'll do is I'm going to plot an array of v's, and here I'm actually just going to plot the PDF. So I get the PDF here. Of course, I'm using NumPy on this side. It doesn't matter. This is just for plotting purposes. And then I'm going to plot the final histogram of the velocities, so the v's, next to the probability density function in both cases. So here, of course, what I'm doing is I'm taking the sum of the squares at the 400th time point, right? So the sum of the squares, that's like square root of vx squared plus vy squared, and then I take the square root, so that gives me the magnitude of the speed. So I'm going to make a histogram of that. In this case, I'm going to use 50 different bins, and in this case, I can only use 10 bins because I have much less statistics. So let's look at the difference of these plots. So here's using those statistics, and here's using these statistics. So you could see that as I simulate more particles, look at that, you get a much better sort of statistics that approach this probability density function. So of course, x-axis is velocity, and this is a PDF. And so a lot of the particles, although they all start at 500, they sort of approach this distribution here. The same thing happens here, but of course, when you have so little bars, it doesn't look great. And I could always add 50 bars if I wanted to, but it's going to be very noisy, right? And also there's less particles. So, in this case, I only have 400 particles, so they're not colliding with each other as often. It's much better to use more particles, and then you get far more statistics as well on your histogram. So finally, let's make an animation of both cases, because I think it's really interesting to look at this. So here I'm going to make the animation with, well, this is 10,000 particles. And I'm not going to run this. So this is another thing as well. This is, again, updated code from the previous video. In this case, I was doing something very slow. Ignore what I did in the previous video, of course. Here I'm using a much more optimized way using blitting. So of course so you can see that blit equals true when I run the animation, and I'm only updating the things that change. So in this case, it's the location of the billiard ball markers. And so you can run both these codes to make the animation, and you'll see this. So again, they initially all start at 500 meters per second, they collide with each other, and then you get this beautiful convergence to this particular distribution function here. So you're basically validating a law of physics. And so, yeah, this is a very simple use case. Like, this isn't going to be modern research or anything. But of course, as soon as you start dealing with particles that have complicated forces between each other and interactions and things like that, they might converge to a different distribution. And that can be interesting for novel research. But the main point of this video is that we had an application where we were doing a simulation that involved many particles. And we used the functionality of PyTorch to massively speed up the computation time of that simulation. So thank you for watching this video. There's going to be much more videos in the series, so I look forward to seeing you next time. Please like and subscribe, of course. Join the Discord server below. Order one of these beautiful t-shirts here with your fellow Billy on it as well. And I'll see you next time.